plus 10 log q by 4 pi r square plus 4 by r. So, if I now change the r, if I change the r, let us say let me change the r is what was r? If I recollect, r was room constant and we said it was S alpha bar divided by 1 minus alpha bar. So, it is a property of the room. This is the total absorption in the room and this is 1 minus average absorption in the room, right. So, this is a property of the room itself, and as you can see, if I increase the r, LP will reduce, particularly if you are away from the source, r is sufficiently large, right. So, you want to you want a noise is generated within the room and you do not want this noise to that source to contribute too much to the noise, then increase the r. So, you will have r 1 and r 2. Let us say I have changed the room constant from r 1 to r 2. So, this is what delta LP will be basically I have changed. So, LP 1 let me call it minus LP 2 will be equals to 10 log W by I ref minus again 10 log W by I ref. This part will cancel out. So, this will cancel out, but this side will be there plus 10 log q by 4 pi r square. For the distance is same 4 by r 1 minus 10 log q by 4 pi r square 4 by r 2. So, this will cancel out and this I can now combine, write it 10 log this divided by this, because it is a logarithm, there is a minus sign. So, that is what we have done, that is what we have done, that is what we do, and that is 10 log q by 4 pi, So, I can write it like this. So, delta LP, LP 1 minus LP 2, initially it was LP 1 and then it changed to delta LP 2 when I have changed the R 1 to R 2. So, this will be the ratio, and if the distance is sufficiently large, only diffused field I am looking at, then simply for diffused field only. So, when r is sufficiently large beyond room radius, I am not really interested in this part, only this part, this will be 10 log 4 by it will be r 2 by r 1, 10 log, because 4 will cancel out, I will be left to 10 log r 2 by r 1, right. So, if I have higher r 2, more r 2, my delta LP reduction will be more, So, I should have more higher room constant, which means I should increase the alpha value, alpha bar value. So, S alpha bar divided by 1 minus alpha bar. So, if I increase this, alpha 2 is greater than alpha 1, alpha 2 is greater than, so alpha 2 is greater than alpha 1, this value will increase and then noise will be controlled. So, that is how it is. So, improving the, if the source is within, one way of improving its, as I said, a typewriter somewhere in a corner or something similar, which may not be, which is kind of a noise for other people who are sitting there in the room, might be an office or similar sort of spaces, something generates noise and you want to control it, then increase the absorption. That is what it says, right. Now, if I know the frequency of the sources, then frequency selective absorptions I can have. For example, you consider this is a simply a porous screen in front. This is a porous screen in front, like something like this holds a screen, a panel, and I have made holes in that. So, that is basically a porous screen. So, this is this is how it is coming. Now, its response alpha value, the absorption coefficient is a is maximum when 4 by d 4 d by lambda, this is distance d, lambda is a wavelength of the sound. So, when 4 d by lambda is equals to 1, its absorption is maximum, or 3, 5 etc., one can show that. So, you see, if my frequency is such that the lambda is such that, so 4 d by lambda should be equals to 1, let us say. In that case, I can find lambda is nothing but C by f. So, if I know lambda, I know f, I can find out f. So, frequency of the source is known. For example, if it is a typewriter, I know its kind of frequency. Remember, we talked of equal loudness level contour, there we showed those frequencies. So, if I know the frequency, lambda will be known to me, velocity is 340 meter per second or close to 340, 344 or whatever it is meter per second. I can find out what should be the d, where I will have maximum absorption. So, I can choose for a porous screen what is the distance, and provided I know lambda. So, that is what it is. So, this at this frequency it will be maximum, or this frequency it will be maximum, other frequencies is less. So, its frequency is selective, there is a bandwidth, but still it is frequency selective, right. So, absorbent material, this remember that this is different than insulation. Insulation is transmission loss, just separate, its absorption will not come back. Absorption high means it will not come back, not necessarily it will not allow it to go other side, because open window has got an absorption is equals to 1, but that will transmit everything to the other side as well. So, that is it. So, d is equals to n lambda by 4, that is the thing, n equals to 1, 3, 5 etcetera etcetera. So, I can determine the d maximum absorption, right. So, alpha 2 will be this value here. If you are you are very sure about this frequency, I mean this frequency you are sure, because lambda is equals to nothing but c by f. So, if you know this frequency you are quite sure of, you can use this kind of an absorber, right. So, that is the idea. Alpha is this value, no. Alpha 1 is what is existing, you want to improve over it by alpha 2, right. No, but if you have designed it well, it is no problem. If you have designed it well, then you choose, that then also if you have actually envisaged or foreseen that there will be some noise sources within the room, you can put right kind of absorber to see that maximum absorption occurs at given frequency, right. So, this improves, supposing I want to improve this, put this is porous material here, there is another way. Now, this porous material is relatively so porous layers make broadband d is equals to lambda by 4. So, it is something like this. So, if it is a porous material, it will be something like this curve for this case. That means, I have a backing wall, I put a porous material on top of it, right. Suppose glass wool, I mean mineral wool, glass wool of course can be a health problem, it can handling, but it is fine, still glass wool people use, there is a thermal insulation also. So, you put some porous material right on top. Now, this porous material, this is the point where beyond 4 d equals to lambda by 4. So, 4 d by lambda, you find that beyond this it is higher frequencies, it absorbs more, and if you have a air gap, then this will be something like this, this will come even so it is much absorption at higher frequencies, very low frequencies absorption is less, not specific frequency. So, this is this is a single layer, something like that, air space was there, air space should make something of this kind. So, air space improves low frequency response. So, if I put an air space here, it improves the low frequency response. If I do not have an air space, just put porous material, you will get something like this, right. And that is how one can so depending upon the type of source you are likely to have, you can use special absorbers. Membrane or panel absorbers, just put a membrane, just put a panel here. So, this will depend upon this d, this will depend upon d, and mass of the material that is here, it could be a porous material as well. So, you have actually d increasing along this direction, you will find that low frequency response increases. This is the mass of this panel here per unit area. So, this membrane or panel absorbers, they can also by and large, although it is broadband, but the peak is somewhere only at a single point. So, if you know the frequency, you can choose the right kind of absorbers. So, membrane mass is m kg per meter square, this is the membrane mass, and this at this frequency it resonates, and therefore, it absorbs maximum energy, because it will vibrate itself, will not allow sound to come back there, right. So, that is what it is, where this is Poisson's ratio, m d is this value. As you increase the m d, frequency reduces, frequency goes down. So, m or d you increase, it will actually this f you reduce, f gets reduced. So, actually if you put a membrane, simple, put a plywood sheet in front, if you are, I am saying if you are diagnosing, right in the planning design stage one can do that, you can choose, what are the kind of sources, and therefore you can choose. So, choose the kind of absorber you want to put, and if it is all random, you do not know the frequencies, you put, there is nothing, this kind of absorber, special absorbers do not work. If you know the frequencies, then this sort of absorbers will work, because it has got a peak at a given point and very high value, while other kind of absorbers just putting casually something like some fiber boards and all, as would have done in this particular case. This will definitely reduce, you see, noise. In fact, like there possibly one should not have put this perforated gypsum boards here, in front of the source. This is all same they have put in. A good acoustic design. See, we are using mic also for such a small room, it is really not necessary if it is done in a proper manner. This should have some amount of reflector, I mean on top of this up to certain point, as we shall see in case of auditorium design, because whatever is spoken here, that should go back to the end. So, if I put a correctly angled reflector, that will send to the end. So, acoustic design, if it is done properly, right in the beginning you can put even special absorbers if you know the frequency of the source, If you do not know, then obviously this kind of special absorbers you can use. They are useful in machines, place where there is a machine, because their frequencies are very well known, right. Speeches it will be very difficult to handle in this manner. This is called Helmholtz resonator. Yeah.
So, the absorptivity is depending upon mass per unit area
of this membrane, mass per unit area of the membrane, this membrane.
So, this particular frequency corresponds to the resonant frequency.
Yeah, they are at the resonant frequency, because of its resonance, it will not allow energy to come back, it will absorb that energy. The membrane itself will resonate, it will vibrate quite a lot and will not pass back that energy to the space. So, it is in a way the structure itself holds the energy together.
So, the hammer kind of thing is the
occurring there in the membrane itself. That is related to the Poisson's ratio of this one, because something is impinging there, then. So, this directional movement, mass and the distance between this one, because air also will resonate together with this. So, this cavity you will have actually high level of sound if you can put a microphone there, but it will not be there into the room outside, here it will be less. So, basically if it is resonating within this column, this area, sound is resonating, forming a standing wave, let us say within, inside is forming a standing wave. In that case you will have high sound level here, but at the space you will have much less. Space is outside, it is within that this space, right. So, I do not mind some resonance there, because I am not going to put someone inside that distance, this distance is relatively small. Similarly, this Helmholtz resonator, it will actually resonate within this, right, but nothing will happen outside, it will not bring. So, a very specific frequency, very narrow band, but actually 100% absorption at a narrow band frequency. So, this is something like this, if this distance is L, cavity, this length is L, this is the area of the cavity, area of the neck of the cavity, then this is given by C is the velocity of sound, A is this area as I am showing, and L is the length of entry, and V is the volume of the cavity. So, this is the volume of the cavity is known. At this frequency you will have almost 100% absorption. You can derive this, one can derive equation for this, but we are not interested in that. So, depending upon this volume, at certain frequency it will it will resonate. So, sound will resonate within this cavity, and this simple Helmholtz resonator, and it will absorb everything, but nowhere else. So, if you know, you can make this actually, you can make this, not a problem. This is the wall, actually this is your wall, there will be another something like this, I mean another sorry, my drawing is not, I am not doing a good job as far as my drawing is concerned. So, it will extend like this, then something of this kind, then there is another one, the wall is something like this, backing wall, etc., etc. So, I have actually holes in the wall, cavities in the wall with the entry. right. So, this is one, there is the next one, and these are all walls, and again there will be another cavity. So, series of cavities in this manner and with a entry point available, right. Now, this kind of thing should specifically absorb at a given frequency given by this formula, depending upon area of the entry and length of the entry and volume of the cavity itself. So, one can derive this formula, but slightly different is if you want to make it broad base, what you do is you have porous material, make this cavity, this itself is the cavity, might put porous material or may not put porous material, but you have holes, larger holes. Earlier we had a perforated one, was very small, there is larger holes, and this formula is again given ABC with varying dA etc. So, this is d, this is area is that same entry radius, spacing is there, this is the spacing. So, formula is given as S as the spacing between two entry center to center, T is the thickness of this one, T is the thickness of this panel in front, and A is the area, this area as I talked about, D is this distance. So, this is relatively broadband, while Helmholtz cavity resonator as it is called is very fixed to a specific frequency. So, one can use that if you know the frequency, otherwise this is broadband, and this this changes depending upon value of A, D etc. you can get different absorptions. So, but they absorb quite a bit, significantly they can absorb 0.9 or whatever it is, high absorptions you can. So, they are used for specific frequencies. Here of course is relatively broader. So, these special absorbers are used in those places where I know the frequency of the source, right, know the frequency of the source, there I can use them, all right. So, that is it. So, that is absorbers. So, I can use those absorbers and control the noise generated within the room itself. If I do not know the frequency, well, generally it will be known because it will be machines or something of that kind, right, it will be machine or something of that kind. If I do not know the frequency, then of course, it is random noise, like in lecture theatres, auditoriums, there we do something different. We rarely use this kind of absorbers. Why? Because frequencies are not known. Supposing it is a multi-purpose auditorium, I can have a speech, I can have music, dramatics, so many things, and there the frequency is varied. So, you have to have broadband, not very specific frequencies, use absorbers which will absorb largely in many frequencies and so on. So, quite often people do it by simple, as I said, just use some board, but it is better to look into absorption coefficient, get the information about absorption coefficient at different frequencies before you apply them into the space that you are interested in, right. So, that is what it is. So, this was related to absorbers. In fact, they give you absorption at 5 different frequencies at mid frequencies of certain octave band, and average of that is specified in many such materials, right, many such materials. Okay. So, that is one way. Many if you are asking for some absorbers to be purchased, they will give you at what are the absorption at different frequencies. Sometimes they give you the average at 5 octave bands, 125, 250, 500 etc., certain octave bands at the center frequencies, what are the absorptions they will give you, and average of that will be given. So, that is called, I think, noise reduction coefficient or something. Okay. So, some they give it. So, all that I am trying to point out, if you want to use them, the source is inside, you want to control that noise, you want to put in absorbers, find out the frequency at which your source are likely to be, it is a known source, and then use that for use that specific frequency related absorption. Now, how much absorption is that frequency? But if it is all different kind, then use as broadband as possible, which should absorb at different frequencies. So, total overall average absorption at different frequencies that you can look into. So, that is related to control of the source if it is within the room, same room. If it is another room, then I should have transmission loss values I should look into. So, that is transmission, and let us look into the transmission tau. How does it depend on tau, partition wall properties? So, basically you can model it like this, I have an incident sound pressure level P I, excess pressure in the air, and there will be some reflection, and we assume for this particular case our walls are mostly very rigid, so that the pressure, reflected pressure and incident pressure, they will be by and large same, but they are acting in the opposite direction. So, net pressure acting onto this will be actually 2 P I, one along this direction and the other is right. Now, this actually sets it the particle in motion, particle within the wall in motion about their mean position of equilibrium, and vibration is transmitted to the solid through this medium, and this in turn causes particle to vibrate, the air particle to vibrate at the other end. That is how the sound is transmitted. So, pressure here will be P T, pressure here is P I, and then reflected is P R, that is force per unit area, and that must be, if I know mass per unit area, that must be the particle acceleration inside, right, and particle velocity inside and particle displacement inside, all three will be there, and that we are as talking about. So, the vibrating air molecule induces acceleration of wall particles, and this results in mass into acceleration, y dot I am calling it, because displacement to use y, if you remember. So, y double dot means acceleration of the particle, m is the mass per unit area, because pressure I am talking of, and y is velocity, and remember, if I have velocity, acoustic pressure must be equals to acoustic impedance multiplied by velocity. So, I have both acceleration and velocity, and this is this is rho 2 rho c y, that's so the 2 P I is the force that is acting here. The particle will move mass and acceleration plus the acoustic impedance into the particle velocity. So, this will be the actually equation of motion there, So, this because you remember P by y dot was equals to rho c, right. So, some component of the pressure, because I have acceleration and velocity together, it is moving and also it is accelerating. So, some component pressure must be balanced by velocity, because medium has got rho c, impedance of the medium is rho c multiplied by the velocity. So, that is the medium, medium related to the medium, and mass of the thing per unit area into acceleration. So, that is a component, both the components will be acting simultaneously, balancing the pressure. A part of it would cause acceleration, part of it would cause velocity, these two things are occurring together. It is accelerating also at any particle, if I take at any point, it is accelerating as well as it has got a velocity. So, corresponding to velocity, depending upon the acoustic impedance of the medium, there will be a pressure component. So, total pressure that is impinging onto the wall must be balanced by some velocity which is occurring of the particle at the place, and also the acceleration part of it. So, that is why we are doing it like that, right. So, I can assume, because this is the solution of this one, if I have pressure, this is the pressure, impinging pressure, and what we are saying is I have got y double dot y dot. So, if I want to find out the solution of this is a second order differential equation, solution of this one, y in terms of rest of the thing, P I is the external pressure that is coming in. So, if I want to find out something like this, y double dot like y double dot plus some mass y double dot rho c y dot equals to some constant P I, whatever it is, 2 P I and so on. So, this is nothing but it is a second order differential equation. So, I can assume y actually will be equals to y some y 0 e to the power I omega t, I mean omega t, the way we do exponential function, Similarly, pressure I can express, because pressure, if you remember that we can relate displacement to the pressure and velocity, they are in the same phase. In the beginning we talked about. So, instead of using y as y is equal, so that is what it is. So, y dot is equals to u and u 0 I omega t. So, we assume, because second derivative of the pressure also will be, wave equation shows us second derivative of the pressure or displacement all will be related in the similar manner. So, what we do is we assume P is equals to P 0 E I omega t. It is periodic, the impinging pressure, sound pressure is is like this, velocity is u 0 I omega t, and y so this is what it is, and y dot is equals to E 0, because y double dot will be given like this. So, I can write it in this manner, because y dot and y double dot, in fact, I could have solved it in a slightly different manner also, but does not matter, this itself is good enough. Everything, since this is periodic, the image, the wave that is impinging onto the surface pressure, this is periodic, and I can assume it to be P 0 I omega t. Velocity is also in phase, therefore, E 0 I omega t. The acceleration will be given in this manner, and I can write this equation. Okay, I could have done something also. Instead of y dot, I could have written it some another variable. Then this will get converted into a first order equation actually, but does not matter, for our purpose this is good enough. So, because this is periodic, this is a general equation, because you will have a cos function as well as I sin function e to the power I omega t. So, what we do is we express it in this manner, and we get P I is equals to, from this we get P I is equals to m I omega by t. If I differentiate and put them, second differential y double dot I put it here, y dot I put it here, P I put it here, then I get P I is equals to m E omega t will cancel out from everywhere. I will have m I omega, right, and there is u 0 is coming here, u 0 is coming here. So, this is taken here, u 0 is taken out here, and m I omega by 2 plus rho c, u 0 is outside. So, this is how I can write for P I. So, pressure, incident pressure can be related in this manner, right, and transmitted pressure is what? Transmitted pressure, because, so what we do is basically the mass acceleration is caused by the force that is coming in. On the other side, other end, it is actually the velocity, transmitted pressure we write in this manner, P c y there, and similarly this also we assume it to be e to the power I omega t multiplied by some amplitude of this, and we can write it in this manner. So, P t is written as P c u 0, P t is written as same as P c u 0, the amplitude of the velocity, and if I take the ratio of this P t by P I, ratio of this P t by P I. So, then I get it in this manner, this divided by this. So, this u 0 will not be there, E I omega t anyway would not be there, and this divided by this part. So, I will get rho c, u 0 will cancel out, rho c by rho c, this P I divided by P c 1 plus m I omega by 2, this is what it will come to. This is what it will come to actually, or let me write it in this manner. If I write it separately, P t by rho c u 0 divided by u 0 multiplied by m I omega by 2 plus rho c. So, this is P t by P I, and rho c if I divide by this will be 1, here I will get rho c, u 0 will cancel. So, I will have m I omega, and P t by P I can write it in this manner. How does it come? So, P c rho c, if I cancel out or take rho c out, yeah, same thing will come. Then P I by P t, P I by P t, this is P t by P I would be here. This is how I will be writing it, J I, that is exactly the thing. So, it comes out something like this 1 by m over. So, P t square by rho c square if I write it, because that will give me the decibel level reduction, it comes out something like this. And if this is too large compared to 1, then I can write it simply at high frequencies, because omega is twice pi f. So, if this is too large compared to 1, then I can write it in this manner at high frequencies, and tau will be equals to, because P t square by P I square is tau, P t square by P I square, this is nothing but tau, this is nothing but tau. So, tau can be written in this manner twice rho c by omega m square. From this one, for at high frequencies twice rho c by omega m square. You see, what we have done is we have neglected several things here. The stiffness part of the thing we have neglected, and at higher frequencies we are dealing with. So, tau can be related to the mass per unit area at high frequencies, that is of our interest. So, when frequency is high, it is proportional to, inversely proportional to mass per unit area, and acoustic frequencies, this value will be sufficiently, this value will be sufficiently large compared to this. Okay. So, we will just break for a minute and come back again.